Welcome to today's session. In this video, we'll be tackling an exciting problem titled Minimum Deletions to Make String Balanced. We'll explore the challenge, break it down step by step, and review an approach to solve it effectively. Let's dive in. The problem asks us to transform a string S, which consists only of the characters at end B, into a balanced string. A string is considered balanced if it does not contain the pattern BA. Essentially, all the characters must come before any B characters in the string. To achieve this, we are allowed to delete any number of characters from the string. The goal is to determine the minimum number of deletions required to make the string balanced. For example, if S is given as a bababab, we need to calculate the smallest number of deletions required to eliminate all occurrences of the undesired BA pattern while maintaining the order of the remaining characters in the string. In the first example, the input string is a bababab. The output is 2, meaning we need to delete 2 characters to make the string balanced. One way to achieve this is by removing the B at index 2 and the at index 6. After these deletions, the resulting string is abab, which is balanced because all the characters appear before any B characters. This demonstrates that the minimum number of deletions required to achieve a balanced string in this case is 2. Similarly, in the second example, if the input is baab, the output is also 2. Here, we can delete the B at index 0 and the B at index 8. The resulting string, baya, is balanced because all remaining characters occur before the B. To summarize the second example, deleting the B at the start and the B at the end ensures there is no BA pattern in the resulting string. The output is 2 deletions. The constraints of the problem specify that the length of the string can be as large as 100,000, and the string will only consist of A and B. It's also important to note that a balanced string strictly follows the format where all A characters precede all B characters. Examples of balanced strings include AAA, BBB, or ABAB. On the other hand, strings like BA, ABAB, or BABA are not balanced. Special cases to consider include strings that are already balanced, strings with only one character, or strings with alternating patterns like abababab. These edge cases will test the robustness of our solution. To solve the problem of minimizing deletions to make a string balanced, we first considered a brute force approach. This method involves iterating over all possible subsets of the string to identify which ones are balanced, meaning they contain no BA pattern. For each subset, we calculate the number of deletions required and return the minimum. While this guarantees correctness, the time complexity is 2 to the power of n, due to the exponential number of subsets. This makes it impractical for larger strings. Next, we explored an optimized approach using prefix and suffix counts. Here, we track the number of B's before each position and the number of A's after it. By iterating through all potential split points, we can calculate the deletions needed to make the string balanced. Specifically, we use a prefix array to count B's up to a given index and a suffix array to count A's from that index onward. The deletions for a split point are simply the sum of these values. This approach achieves a time complexity of O(n) and space complexity of O(n), making it significantly more efficient than brute force, though it does require extra space for the arrays. Building on the prefix-suffix idea, we then developed a single-pass approach with dynamic tracking, which is even more efficient. Instead of using arrays, we rely on 2 variables. The first, count_b, keeps track of the number of B's encountered so far in the string. The second, min_deletions, dynamically records the minimum deletions required at any point. As we iterate through the string, if we encounter an A, we have 2 choices: either delete the current A, which increases min_deletions, or delete all previous B's, which resets min_deletions to the value of count_b. By updating these variables dynamically, we can efficiently compute the minimum deletions needed. This approach runs in O(n) time and uses O(1) space. While it's the most efficient solution, it requires careful implementation to ensure correctness. The chosen strategy for this problem is the single-pass dynamic tracking approach. The intuition behind this method lies in the observation that a balanced string consists of all B's followed by all A's. To achieve this, any N appearing before any B must be deleted, and any B appearing after an A must also be deleted.
Instead of explicitly splitting the string, we track the number of Bs encountered as we iterate and dynamically update the deletions required when encountering As. This approach is preferred because it combines simplicity with efficiency. By avoiding the need for additional arrays, it reduces space usage while still achieving the desired result in a single pass. This makes it particularly suitable for large input sizes, such as strings of up to 100,000 characters. The method builds on the prefix-suffix concept but streamlines it, reducing overhead and ensuring optimal performance. While the single-pass dynamic tracking approach is highly efficient, it does come with some trade-offs. Compared to the prefix-suffix approach, it saves space by eliminating the need for additional arrays, but it may be less intuitive to understand initially. On the other hand, the brute force method, while straightforward in concept, is completely infeasible due to its exponential time complexity. In conclusion, the single-pass dynamic tracking approach is the optimal choice for this problem. It achieves the best balance of time and space efficiency while maintaining correctness and clarity, making it the most practical solution for handling large strings effectively. To solve this problem, we need to determine the minimum number of deletions required to make a string balanced, or a balanced string ensures that no B appears before any A. For instance, UB is already balanced, but BA is not. The input is a string composed of only A and B characters, and the output is the minimum number of deletions required to satisfy this condition. A key observation is that a balanced string can be thought of as having all A's grouped together before any B's. This means we can split the string at various points and calculate the cost of converting the left part into a valid B segment and the right part into a valid A segment. For each division, we count how many characters need to be deleted to achieve this configuration. This insight helps us frame the problem in terms of minimizing deletions across all possible split points. The dynamic programming approach is optimal for this, as it allows us to incrementally calculate the minimum deletions while reusing results from previous computations. We define dp, I, as the minimum number of deletions needed to make the first I characters of the string balanced. The base case is straightforward. For an empty string, no deletions are needed, so dp, 0, equals 0. For each character in the string, we consider its contribution to the balanced string. If the character is A, it can naturally be part of a balanced string, meaning no new deletions are required, so dp, I, equals dp, I1. If the character is B, we have two choices. We can either keep this B, which means we need to delete all A's before it, or we can delete this B entirely, continuing with the deletions needed for the previous state. This gives us the transition formula, dp, I, equals min, dp, I1, plus 1, count underscore A underscore before underscore I plus count underscore B underscore after underscore I, where count underscore A underscore before underscore I and count underscore B underscore after underscore I help track how many A's or B's would need to be deleted. To compute this iteratively, we initialize these counters and update them as we move through the string. Edge cases include an empty string, which requires 0 deletions, a string with only one character type, which is already balanced, and strings like ABAB, which also require no deletions. The power of this approach lies in avoiding brute force by leveraging the prefix-suffix structure of the string. Instead of checking all possible substrings, we use the dynamic programming array to build the solution incrementally. The DP array stores the minimum deletions needed up to each index, and the counters count underscore A underscore before underscore I and count underscore B underscore after underscore I ensure that we can calculate deletions efficiently as we traverse the string. This approach has a time complexity of O(n), because we make a single pass through the string while updating the necessary counts and DP values. The space complexity is also O(n), due to the DP array. However, this can be optimized further, as we'll see shortly. To summarize, dynamic programming and prefix-suffix calculations allow us to solve the problem efficiently without redundant computations. To optimize the space complexity, we can eliminate the need for the full DP array by using a single variable to store the result of the previous state. This reduces the space complexity from O(n) to O(1), as we only keep track of the current and previous values needed for the computation. By iteratively updating this single variable, we maintain the efficiency of the algorithm without additional memory overhead. The time complexity remains O(n), since we still make only one pass through the string. With these optimizations, the algorithm becomes both time and space efficient, making it well suited for large inputs. This completes the dynamic programming solution,
providing an optimal way to determine the minimum deletions required to make the string balanced. This Python implementation is designed to solve LeetCode problem number 1653, minimum deletions to make string balanced. The goal is to determine the minimum number of deletions needed to make a string balanced, or a string is balanced if it does not contain the substring BA. Explanation of the code.
1. Initialization.
We initialize two variables.
Min_deletions to track the minimum deletions required as we iterate through the string. Count_A to store the total number of characters in the string.
This helps us keep track of how many A's are still to be processed.
2. Iterate through the string. For each character in the string, we consider two scenarios. If the character is a, we decrement count_A since we have processed one A. If the character is B, we have two choices. 1. Delete this B, which increases min_deletions by 1. 2. Keep this B and instead delete all future A's, represented by count_A.
The minimum of these two choices determines the updated value of min_deletions.
3. Result.
After processing all characters, min_deletions contains the minimum number of deletions required to make the string balanced.
Key insights.
By maintaining a running count of the A's and dynamically updating min_deletions, we ensure an efficient solution with a single pass through the string, O(n) time complexity. The min function allows us to balance the trade-off between deleting B's early or deleting A's later, ensuring we always make the optimal choice at each step. This implementation is efficient, concise, and handles all edge cases, such as strings composed entirely of A's or B's, or empty strings. Here, we define the method minimum deletions, which takes a string S as input. First, we initialize two variables, min_deletions to track the minimum number of deletions required, and count_A to keep track of the total number of characters seen so far. We then use a loop to iterate through each character in the string, counting the total occurrences of A in count_A.
Next, we process each character again.
If the current character is A, we decrement count_A to reflect that one A has been processed. If the character is B, we have two choices, either keep the B, leaving min_deletions unchanged, or delete the B, which would effectively reduce the number of B's appearing before A. To ensure we take the optimal approach, we update min_deletions to the smaller of its current value plus 1 or the remaining count of A.
This ensures we are minimizing deletions while maintaining a balanced sequence.
Finally, after iterating through the entire string, we return the value of min_deletions, which represents the minimum number of deletions required to make the string balanced. By balancing the trade-off between removing B's and the remaining A's, this approach ensures an optimal solution while maintaining efficiency with a time complexity of O(n). Here, we begin with the first example where the input string is a bababab. To solve this, we initialize two key variables, min_deletions is set to 0, which will track the minimum deletions needed, and count_A, which counts the total number of A's in the string.
For this input, count_A is 4. Now, as we process each character in the string, we start with the first two characters, both A.
Each time we encounter an A, we reduce count_A by 1, since we are essentially saying this A has been processed.
Importantly, since there are no B's before these A's, min_deletions stays at 0. When we reach the third character, which is a B, we now have to decide, do we delete this B to maintain balance, or should we delete an A later on? The optimal choice here is to calculate min_deletions plus 1, count_A, which gives us 1. We repeat this process for the rest of the string, updating count_A and min_deletions as needed.
For example, when we process the fourth character, another A, we reduce count_A to 1 but keep min_deletions unchanged at 1, since this A doesn't disrupt the balance. Continuing with the string, the fifth and sixth characters are both B. For each of these B's, we calculate min_deletions plus 1, count_A, which remains 1 because it's still better to keep the B's rather than delete A's. When we reach the seventh character, an A, we reduce count_A to 0, as we've now processed all the A's in the string. At this point, min_deletion stays the same at 1 because the A doesn't require any additional deletions.
Finally, the eighth character is a B. At this point, since count_a is already 0, we calculate min_deletions plus 1, count_a, again, which confirms that min_deletions remains 1.
With all characters processed, the final output for this example is min_deletions equals 1, meaning only one deletion is required to make the string balanced.
In the second example, the input string is Baba.
As before, we start by initializing min_deletions to 0 and calculating count_a, which is 4 since there are 4 a's in the string. The first two characters are both b. For the first b, we calculate min_deletions plus 1, count_a, which gives us a min_deletions value of 1. For the second b, we perform the same calculation, and now min_deletions becomes 2 because we're adding another b to the string. Once we start processing the a's, which begin at the third character, we reduce count_a by 1 for each a. Importantly, since the a's do not disrupt the balance after the earlier b's, the value of min_deletions remains fixed at 2 for all the a's processed. For example, when we process the third and fourth characters, both a count_a decreases to 3 and then 2, but min_deletions stays at 2.
The process continues with the last two characters of the string, both a.
For each of these, we decrement count_a by 1, reducing it first to 1 and then finally to 0.
Throughout this, min_deletions remains unchanged at 2, as no additional deletions are needed to maintain balance. With all characters processed, the final output for this example is min_deletions equals 2.
This means that, in this case, 2 deletions are required to make the string balanced. Now, let's look at the third example, where the input string is a bab. Here, we begin by initializing min_deletions to 0 and counting the total number of a's in the string, which gives us count_a equals 2 since there are 2 a's present.
Processing this string, we start with the first character, an a.
Since it's an a, we reduce count_a by 1, leaving 1 remaining a, and min_deletions stays at 0 because there's no b before it.
The second character is a b, so we calculate min_deletions plus 1, count_a, which gives us 1, updating min_deletions to this value.
The third character is another a, so we reduce count_a to 0, and min_deletions remains 1.
The next three characters are all b. For each of these, we calculate min_deletions plus 1, count_a.
Since count_a is now 0, min_deletions stays at 1 for each calculation. After processing all characters, the final output for this example is min_deletions equals 1, meaning only one deletion is needed to balance the string.
This concludes the walkthrough of the examples.
The time complexity of this solution is O(n), where n represents the length of the input string.
Let's break this down step by step.
First, the operation s.count scans through the entire string to count the occurrences of the character a. Since this involves iterating through all n characters, it takes O(n) time. Next, the algorithm uses a for loop to traverse the string once more. During each iteration, it either decrements the count_a variable if the character is a, or updates the min_deletions variable using the min function if the character is b. These operations inside the loop, such as comparisons or updating variables, are constant time operations, or O(1). Because the loop iterates through the string exactly once, this step also has a time complexity of O(n). When we combine these two steps, the total time complexity of the solution is O(n) plus O(n), which simplifies to O(n). The space complexity of the solution is O(1), meaning it uses constant space regardless of the size of the input string.
Let's examine why.
The algorithm employs two integer variables, min_deletions and count_a, to store intermediate results. Since these variables occupy a fixed amount of memory, they require O(1) space. Additionally, the input string s is only read and not duplicated or modified, so no extra space is allocated for processing it. Finally, the solution does not rely on any additional data structures, such as arrays, stacks, or hash maps, which might otherwise consume additional memory. By avoiding these, the algorithm ensures that it operates within constant space.
Therefore, the overall space complexity remains O(1). Now let's analyze the algorithm under different scenarios.
In the best case, the string is already balanced, such as having all a's followed by all b's. Even in this scenario, the algorithm scans through the entire string to verify its structure, resulting in a time complexity of O(n). In the average case, which involves a random mix of A's and B's, the algorithm still processes each character exactly once, so the time complexity remains O(n). For the worst case, where every character needs consideration, for example, when the string alternates between A and B, the time complexity is still O(n), as the algorithm does not perform any additional work beyond the single pass through the string. To compare, a brute force approach might involve generating all possible subsequences of the string and checking each one for balance. This would be incredibly inefficient, with a time complexity of O(2 to the power of n, due to the exponential number of subsequences, and a space complexity of O(2 to the power of n, to store them. Clearly, the optimized solution is far more efficient. The current solution is optimized because it avoids generating subsequences altogether. Instead, it uses a single pass through the string while maintaining counters. This approach achieves a time complexity of O(n) and a space complexity of O(1), making it significantly faster and more space efficient than a brute force method. To mathematically confirm the linear time complexity, we note that counting the characters requires one traversal of the string, which is O(n). The subsequent for loop also iterates through the string once, contributing another O(n). Since there are no nested loops or recursive calls, the total complexity is simply the sum of these operations, O(n) plus O(n), which simplifies to O(n). Furthermore, all operations inside the loop, such as comparisons and variable updates, are constant time operations, or O(1), and do not impact the overall complexity. Overall, this solution is optimal for solving the problem with the minimum possible time and space requirements. When tackling this problem, there are some common mistakes to be aware of. First, ignoring edge cases can lead to incorrect solutions. For example, consider cases like an empty string, single character strings, or strings that are already balanced. These scenarios often get overlooked but are critical for thorough testing. Next, if you're using a brute force method, mistakes in subset generation can occur, such as missing certain subsets or handling duplicates improperly. Ensuring that your subset generation accounts for all possibilities is key. Another frequent mistake is overlooking the optimal substructure property, which is common in problems like this. This means failing to recognize that a dynamic programming approach could simplify the solution and make it more efficient. Similarly, brute force methods, while functional, often run into exponential time complexity, which is impractical for large inputs and can result in time limit exceeded errors. Lastly, string manipulation errors, such as incorrect slicing or deletion operations, are common pitfalls. Double-checking indices and ensuring accurate operations can save you from unintended results. Now, let's focus on some insights that can help you during interviews. Recognizing patterns is essential, as many string problems involve recurring sequences, like identifying BA in this case. Spotting these patterns early can streamline your thought process. For problems requiring minimum deletions, dynamic programming is often a strong choice. Using a 2D DP table or state-based transitions can significantly reduce time complexity while providing clarity in your approach. Additionally, some variations of this problem can be tackled with greedy algorithms. For instance, processing the string in one pass while maintaining counts of A and B can lead to a simpler and more efficient solution. Pre-computation techniques, such as building prefix or suffix arrays, are also valuable for optimizing performance. These techniques allow you to pre-compute useful data that simplifies subsequent operations, especially for larger inputs. Exploring related problems can deepen your understanding and help you identify connections between challenges. For instance, LeetCode 1249, minimum remove to make valid parentheses, shares the concept of removing characters to satisfy a condition, making it a useful problem to review. Similarly, LeetCode 583, delete operation for two strings, involves minimizing operations to make two strings identical, which is closely tied to the idea of minimizing deletions. LeetCode 516, longest palindromic subsequence, emphasizes pattern recognition and deletion minimization, offering further insights into dynamic programming approaches. Lastly, LeetCode 1937, maximum number of points with cost, highlights optimization techniques in dynamic programming, which can inspire efficient solutions. Speaking of alternative approaches, dynamic programming remains a powerful tool. For this problem, you could use a 2D-DP table where each entry tracks the minimum deletions needed for a specific substring. This method is more efficient than brute force, with a time complexity of O(n squared), though it does require additional space for the table. Another effective approach is the greedy method. By traversing the string and maintaining counters for at NB, you can efficiently detect and handle BA patterns, incrementing a deletion count as needed. This method is highly efficient with a time complexity of O(n), but it may not work well for more complex variations of the problem. Finally, there's the recursive approach with memoization. Here, you explore all possible deletions recursively, while using memoization to store results of overlapping subproblems. This balances simplicity and efficiency, as it avoids redundant calculations, but it can still be slower for very large inputs. Choosing the right approach depends on the constraints and variations of the problem, so it's important to understand the trade-offs involved with each method. Great work! We've successfully reviewed the problem and explored a solution. Remember, this is just one approach, and there are often ways to optimize further. Keep practicing similar problems to improve your skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!